Preparing for a data engineering at Elastic interview? You've reached Candy Mentor, and this video is for you. We'll walk through 20 key questions you're likely to face. For each question you'll see a sample answer followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you design a reliable data pipeline for Elastic's observability data? I would separate ingestion, buffering, transformation, indexing, and serving layers. Agents or Kafka would absorb bursts, while stateless consumers validate events, enrich them, and write to Elasticsearch using bulk requests. I would design for at least once delivery, make event identifiers usable for deduplication, and send malformed records to a dead letter path. Metrics would cover lag, throughput, rejection rates, and freshness. This architecture protects Elasticsearch from spikes while preserving replayability and operational visibility. While answering, focus on ingestion volume, schema evolution, delivery guarantees, backpressure, partitioning, monitoring, replayability, and how Elasticsearch, Logstash, Beats, or Kafka could fit into the architecture. Question 2. What is the difference between Elasticsearch and a traditional relational database? Elasticsearch is a distributed search and analytics engine built around indexed JSON documents, especially inverted indexes for fast text and filtering queries. A relational database organizes normalized tables and provides mature joins and transactional guarantees. I would choose Elasticsearch for log analysis, full text search, and high-volume analytical retrieval, but not as the default system for complex transactional updates. The right design often uses both, with a relational source of truth and Elasticsearch as a search-oriented projection. Make sure to cover inverted indexes, JSON documents, flexible schemas, distributed search, transactions, joins, consistency trade-offs, and when relational databases remain preferable for highly structured transactional workloads. Question 3. Explain how Elasticsearch indexing works and why mappings matter. When a document is indexed, Elasticsearch analyzes eligible fields and builds structures that make searches efficient. Mappings define how each field is interpreted, such as text for analyzed search, keyword for exact matching and aggregations, or date for time-based queries. I prefer explicit mappings for important production fields because an incorrect inferred type can create failed queries or force reindexing. Mapping decisions affect storage, relevance, aggregation behavior, and long-term schema stability. In your answer, talk about documents, fields, analyzers, inverted indexes, dynamic versus explicit mappings, keyword versus text types, immutable field types, and the operational cost of mapping mistakes. Question 4. How would you handle schema evolution in an Elasticsearch data platform? I would treat schemas as versioned contracts rather than allowing uncontrolled field creation. Additive changes are usually safe, but type changes require a new field or index. I would update templates, deploy readers that understand both versions, and use a write alias during migration. For major changes, I would reindex into a new index, validate counts and representative queries, then atomically switch aliases. This minimizes downtime and protects downstream dashboards and alerting. Be sure to mention versioned schemas, compatible changes, aliases, index templates, rolling migrations, reindexing, validation, backward compatibility, and coordination between producers, consumers, and dashboards. Question 5. What strategies would you use to optimize Elasticsearch query performance? I would begin with the query profile and workload metrics rather than guessing. I would move exact predicates into filter context, request only needed fields, avoid leading wildcards, and use time-based indices for observability data. I would review shard sizing and reduce unnecessary fanout. For deep pagination, search after is preferable to large offsets. Finally, I would benchmark representative traffic, because an optimization is only useful if it improves latency without creating unacceptable indexing or memory costs. Focus on selective filters, query versus filter context, source filtering, appropriate shard counts, index sorting, avoiding expensive wildcards, pagination strategy, caching, profiling, and measuring latency under realistic load. Question 6. How would you design an ingestion pipeline that handles duplicate events? I generally assume at least once delivery because retries and consumer restarts are normal. If the producer supplies a stable event ID, I would use it as the Elasticsearch document ID or maintain a deduplication key. Retries then overwrite the same logical document instead of creating duplicates. For events without stable identifiers, I would construct a deterministic key only when the business semantics support it. I would also monitor duplicate rates and distinguish harmless retries from conflicting updates. In your answer, discuss at least once delivery, deterministic event IDs, idempotent writes, retry behavior, update versus create semantics, deduplication windows, and the trade-off between correctness, storage, and processing complexity. Question 7. What is your approach to partitioning and scaling a high-volume streaming pipeline? I would choose a partition key that distributes traffic evenly while preserving ordering where the business requires it. For logs, a host or service identifier may preserve local sequence, but I would test for hotkeys. Consumer parallelism should align with partition count and downstream capacity. I would monitor lag, rebalance frequency, and per partition throughput. If Elasticsearch becomes the bottleneck, buffering alone is insufficient. I would tune bulk sizes, concurrency, shard layout, or retention policy. Make sure to cover partition keys, ordering requirements, consumer parallelism, hot partitions, rebalancing, throughput limits, backpressure, and choosing whether ordering or even distribution is more important. Question 8. How do you ensure data quality in a distributed data pipeline? I define quality checks close to the data contract, required fields, valid timestamps, accepted enumerations, type correctness, and reasonable ranges. Records that fail should be quarantined with enough context for replay, not silently discarded. I also monitor freshness, volume changes, null rates, duplicate rates, and reconciliation totals between stages. Ownership matters, so alerts should identify the responsible producer or pipeline. These controls turn data quality from a manual investigation into an observable operating process. Discuss validation at ingestion and transformation stages, required fields, type checks, uniqueness, freshness, volume anomalies, reconciliation, quarantine paths, ownership, and actionable data quality monitoring. Question 9. Explain the difference between text and keyword fields in Elasticsearch. A text field is analyzed into tokens, making it suitable for relevance-based full-text search. A keyword field keeps the entire value intact, which supports exact matching, sorting, and aggregations. For a product name, I might use text for search and a keyword subfield for grouping or sorting. I would not use text for identifiers such as trace IDs. Choosing incorrectly can produce confusing results, such as failed aggregations or searches that match individual words unexpectedly. While answering, explain analysis and tokenization, exact matching, sorting, aggregations, multi-fields, case sensitivity, storage implications, and how selecting the wrong type affects search results. Question 10. How would you troubleshoot a sudden increase in Elasticsearch indexing latency? I would first establish whether latency comes from clients, network transport, or Elasticsearch itself. Then I would inspect indexing thread pool rejections, bulk response times, CPU, heap, garbage collection, disk utilization, merge activity, refresh pressure, and shard distribution. I would compare the incident with recent mapping, query, deployment, or traffic changes. Short-term actions might reduce refresh frequency or throttle producers, but the lasting fix should address the limiting resource rather than merely adding retries. Be sure to mention symptom isolation, cluster and node metrics, thread pools, refresh and merge pressure, disk watermarks, rejected requests, shard distribution, bulk sizing, and recent deployment or workload changes. Question 11. Describe a data pipeline failure you would expect and how you would recover from it. A realistic failure is a consumer deployment that writes some batches successfully before crashing. I would rely on committed offsets only after successful downstream acknowledgement, then replay the uncommitted batch. Idempotent document IDs prevent duplicate effects. Invalid records would go to a dead letter stream, while metrics and alerts would expose lag and error rates. After recovery, I would identify the trigger, add a regression test, improve deployment validation, and document the operational runbook. In your answer, talk about failure detection, checkpointing, replay, dead letter records, ID impotency, partial writes, incident communication, root cause analysis, and preventing recurrence through tests or safeguards. Question 12. How would you choose between batch processing and stream processing? The decision depends primarily on freshness and processing semantics. I would use streaming when alerts, operational dashboards, or user-facing search require seconds-level latency. Batch is often simpler and cheaper for daily aggregation, historical backfills, or workloads tolerant of delay. A hybrid approach can combine streaming for provisional results with batch reconciliation for correctness. I would also consider event time handling, replay requirements, state management, and the team's ability to operate another always-on distributed system. Focus on latency requirements, event time behavior, cost, complexity, replayability, data completeness, windowing, operational burden, and whether consumers need immediate results or periodic reconciled outputs. Question 13. What are Elasticsearch shards and replicas, and how would you size them? A primary shard owns a portion of an index, while replicas provide redundancy and conserve searches. More shards increase parallelism, but every shard consumes memory and coordination overhead, so excessive fragmentation hurts performance. I would estimate data growth, retention, compression, indexing rate, query concurrency, and recovery targets before choosing a layout. I would validate the estimate with load tests and monitor shard size, queuing, heap usage, and rebalance behavior after launch. Make sure to cover primary shards, replicas, parallelism, failure tolerance, shard size, indexing and query load, retention, growth forecasts, rebalancing, and why too many small shards are harmful. Question 14. How would you build an observability solution using Elastic Stack components? I would collect logs, metrics, and traces through Elastic agents or compatible shippers, route them through integrations or Logstash when parsing and enrichment are needed, and index them using consistent ECS-aligned fields. Elasticsearch would support search and aggregations, while Kibana would provide dashboards, investigations, and alerts. I would define retention and tiering based on access patterns, protect sensitive fields, and monitor pipeline health so the observability system remains trustworthy during incidents. Discuss data collection, agents or beats, Logstash, Elasticsearch, Kibana, parsing, enrichment, ECS alignment, dashboards, alerting, retention tiers, and securing sensitive telemetry. Question 15. How do you design for exactly once processing when the infrastructure provides at least once delivery? True exactly once delivery is difficult across independent systems, so I target exactly once effects. I use deterministic identifiers, idempotent writes, and checkpoint advancement only after successful output. Where multiple side effects must agree, I would use a transactional outbox or an equivalent coordinated design. I would explicitly document the guarantee, because deduplication state can expire and external APIs may not be idempotent. The practical goal is recoverable processing with no business-level duplication. In your answer, distinguish exactly once effects from exactly once transport, explain ID impotency, deterministic keys, transactional boundaries, deduplication state, and why external side effects complicate guarantees. Question 16. What is your approach to securing data pipelines and Elasticsearch clusters? I would secure each layer independently using strong service identities, least privilege roles, encrypted transport, and centrally managed secrets. Producers should have only the index permissions they need, while analysts receive controlled read access. I would classify and minimize sensitive fields, apply masking or field-level controls where appropriate, and retain audit logs for access and administrative actions. Network segmentation, certificate rotation, vulnerability scanning, and tested incident procedures complete the control framework. Be sure to mention least privilege, authentication, authorization, encryption in transit and at rest, secrets management, network controls, field protection, audit logging, and handling personally identifiable information. Question 17. How would you test a data engineering pipeline before production deployment? I would test transformations with deterministic unit cases, then validate producer contracts, mappings, indexing behavior, and queries in an isolated integration environment. Representative data should include malformed records, large payloads, late events, duplicates, and schema changes. I would load test throughput and latency, inject downstream failures, and verify replay and recovery. Before release, I would define acceptance thresholds, deploy gradually, monitor key metrics, and maintain a rollback or alias switch plan. Focus on unit, integration, contract, property-based, load, failure injection, data quality, and end-to-end tests, plus representative fixtures, performance thresholds, rollback plans, and deployment observability. Question 18. How would you process late arriving or out-of-order events? I would preserve the event timestamp separately from ingestion time and base business windows on event time. For streaming aggregations, I would define an allowed lateness policy and watermark, then update results when delayed events arrive within that boundary. Events arriving later could trigger correction jobs or remain in a reconciliation path. Dashboards should distinguish provisional from finalized metrics. The design must also be idempotent, because reprocessing late data should correct totals without multiplying them. In your answer, cover event time versus processing time, watermarks, allowed lateness, mutable aggregations, correction strategies, idempotency, windowing, and the effect of delayed data on dashboards and alerts. Question 19. Tell me about a time you improved a data pipeline's cost or performance. In one pipeline, indexing cost rose while freshness deteriorated. I profiled the workload and found tiny bulk requests, excessive replicas during backfills, and unnecessary source fields. I increased bulk sizes within memory limits, temporarily adjusted replica strategy, reduced indexed payloads, and scheduled backfills away from peak traffic. Indexing throughput improved materially and storage fell, while validation confirmed unchanged record counts and query behavior. I would present the baseline, measured outcome, and safeguards rather than claim optimization without evidence. Make sure to structure the response with context, baseline metrics, diagnosis, specific intervention, measured result, trade-offs, and how you verified that improvements did not reduce data quality or reliability. Question 20. How would you design a scalable data platform for Elastic's cloud products? I would design the platform around isolated, observable workloads with automated capacity management. Tenant-aware quotas, rate limits, and routing would limit noisy neighbors, while stateless ingestion services scale horizontally behind durable buffers. Data would use appropriate shard and lifecycle policies, with encryption and regional recovery aligned to customer requirements. I would expose service-level metrics for ingestion delay, query latency, errors, and cost. Automation should handle provisioning, upgrades, rebalancing, and safe rollback. Discuss multi-tenancy, isolation, horizontal scaling, regional resilience, noisy neighbor controls, lifecycle management, observability, automation, security, and balancing customer experience against infrastructure cost. If you are still with us, congratulations, you are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.